Welcome to our second video in our geometric reasoning and geometry course. This video will focus on the theories of learning regarding geometric teaching and geometric reasoning, and will also then focus on the big ideas in geometry. Now, the big ideas are huge. We need to bear them in mind as teachers whenever we teach any mathematics. But we'll get to that in a second. First of all, I want to look at Piaget's theory of learning geometry. Now, that's the guy with a pipe in his mouth when it was still fine to smoke. Okay, so Piaget and his colleagues and the Van Hillers are probably the most well-known contributors to the theories of learning. In South Africa, we have two people that has contributed also significantly. The one is Dr. Rita van Niekerk. She's now at the Northwest University, who wrote the curriculum for geometry for our schools in South Africa. And then Professor Michael de Villiers, who was all over. He was teaching at Stellenbosch University and UKZN. They have made major contributions, especially Professor de Villiers. He's world-renowned as a theorist in geometric reasoning and geometric thought. And if you Google him, just Google Michael de Villiers, you will see he's a very generous person. You'll go to his geometric web page where he posts everything available to teachers, freely available, if I may say, to teach geometry with. So let's focus on what Piaget's two themes were. First theme for Piaget was, he said that our mental representations of space is not a perceptual reading off of what is around us. Rather, let me just get my highlighter, we build up, he says, from our mental representations of the world through progressively reorganizing our prior active manipulation of that environment. So he is talking about the way that space around us is organized. And he says we built up our mental representations of that world through progressively reorganizing our previous active manipulation of that environment. So that gives us the idea that geometric thinking and reasoning is a dynamic process which starts at a point and continues to grow. His second theme, he says, the progressive organization of these geometric ideas follows, this is important, he maintains it follows a definite order, and this order is more experiential and possibly more mathematically logical than it is historical. The key thing that he mentions here is the fact that it is experiential, meaning that that development is mainly an experiential development. It is based on the experience of the person who's learning geometry. Okay, so the theories of learning there has two themes, Piaget's themes. Process and information of spatial representation. And secondly, that progressive organization of geometric ideas follows a definite order which is experiential. Okay, two very big, not big ideas, but contributions from Piaget, those two themes related to the learning of geometry. The first of these Piagetian themes, concerning the process of information and spatial representations, remains reasonably well supported by research. It is the second hypothesis, at best, that received mixed support. The available evidence suggests that all types of geometric ideas appear to develop over time, become increasingly integrated and synthesized. Okay, so it's not so much based on the experience, but the fact that it develops over time and then becomes increasingly sophisticated and synthesized and integrated with one another. So you can put yourself in that situation and think, what is the role of the teacher in this? Is the teacher that important to develop this reasoning? Well, then enter the Van Hillers. Pierre and his wife, they both studied under the same supervisor, Hans Freudenthal, and their key study was performed in 1950. The Van Hiller model suggests that learners advance through levels of thought in geometry. The Van Hillers characterize these levels as visual, descriptive, abstract, relational, and formal deduction. Now that takes that second phase that Piaget has spoken about, and it opens it up. It says, how is this happening? I think the Van Hillers must have sat there with Piaget's model and thought, but how does this play out in reality? Okay, according to their model, progress from one Van Hiller level to the next is more dependent upon the teaching method than the experience and the age of the learner. Now this is key. This is where the difference happens. Let me just get my highlighter and let's highlight that. Progress from one level to the next is more dependent upon the teaching method than the age or the experience of the learner. Okay, let's see. Given traditional teaching methods, research suggests, folks, and this is key, that most lower secondary students, now we're talking about grade 8, grade 9, grade 10, perform at levels 1 or 2 of the Van Hiller model, which we will go in depth in the next video. With almost 40% of students completing secondary school, that is going right through secondary school, past matric, and only being on or below level 2 of the Van Hiller model. Now that is very interesting, because you'll see as we study the model, level 2 is the first 3 components of the Van Hiller model. The last 2 components, which is what a learner needs to be able to reason effectively in the geometry class, is thus underdeveloped or not developed at all. Okay, so the explanation for this, according to the Van Hillers, is that teachers are asked to teach a curriculum that is at a higher level than what the students are. Now, folks, don't misunderstand that statement. It doesn't mean the curriculum is too difficult. There's nothing wrong with the curriculum. What it does say is that the teachers, maybe in grade 10, 11, and 12, are teaching geometry at level 3 and level 4 Van Hiller model, while the kids are only at level 1 and possibly at most at level 2. Okay, so that means we start off with the theorem, we teach the theorem, and immediately we apply the theorem. There's no space left for doing things that are necessary to develop the modes of reasoning geometrically in the classroom. According to the Van Hiller model, it is not possible for learners to bypass a level. And that is key. That means that if we start teaching on a level 3 or a level 4, and a child is still on level 1, that child is lost in your geometry class. That child is not afforded the opportunity to learn geometry the way it's supposed to be taught and supposed to be understood, because we are at a different level. And we're going to explore in the videos that come how we can overcome this. And that is going to be spoken about when we talk about the levels, but also when we talk about what the Van Hillers have formulated as their phases of learning. So there's exciting work ahead. Learners cannot see what the teacher sees in a geometric situation, and therefore not gain from such teaching. And as a teacher, folks, you need to be sensitive to that. You need to analyze the learners by asking very pointed and very carefully planned questions to ascertain on which level of geometric reasoning your audience find themselves. Okay, having said that, let's now look at the big ideas in the teaching and learning of geometry. Now folks, these ideas are not just exclusive to geometry, but they are taught in geometry, and they are applied across different contexts in the schooling curriculum. They are applied in art. They are applied in technical drawing or machine drawings, or ECD as they call it now. They are applied in the geography class. They are applied across the different disciplines in mathematics itself. Okay, the order to teach geometry most effectively and give some coherence to classroom tasks. It is helpful in your preparation as a teacher to keep in mind and highlight where applicable and where possible the big ideas in geometry. Folks, it will get you excited when you teach maths, and I hope that one day when you see this in a diagram you think about what we are discussing here and how it informs what you're going to do. The first big idea that we're talking about is invariance. Geometry is the study of the properties, let's highlight that, of the properties of a configuration. I lost my highlighter. Properties of configuration that are invariant under certain transformations. Now the word invariant means does not change, remains the same. Okay? So that is the study of invariance. As I transform this figure, what stays the same and what changes? Big idea in mathematics. Learners do not always find it straightforward to determine which particular properties are invariant. Therefore, as a teacher, you must be tuned into this big idea, and you must, if the kids don't bring it up, you must bring it up in your classroom discussion and highlight what just happened. The use of dynamic geometry software like Sketchpad or GeoGebra or Fathom can be very useful in this respect. Now, remember I mentioned Professor Michael de Villiers. On his website, there's a link to Geometer's Sketchpad, which is now freely available online. Now, you'll find that different software packages allows you to do different things in the maths class. So play around with those software packages and see which one does what for you. You might want to use a mixture of the two. But using the dynamic geometry software in class is not even a question. Folks, it helps developing the geometric reasoning and the visual, I want to say visual literacy of looking at a geometric situation. Okay, the second big idea in mathematics is the idea of symmetry, folks. This is big. You find symmetry in the geometry classroom. You find it in the trigonometry classroom. You find it when you do algebra, when you study analytical geometry. Mathematical figures possess symmetry. Symmetry describes how a mathematical object behaves. Just think of the parabola, for instance. This axis of symmetry chops it in half. It's a mirror image. In more real-life application, think about your favorite actors and why they are your favorite actors. Somebody like Charlize Theron or Nicole Kidman, or male actors Brad Pitt, or even what's the latest guy that's starring, I can't even think about him now, Christopher Evans. Go and look at their faces, analyze their faces, folks, and look at the geometric properties that are present in their faces. It's almost perfect symmetry. That is why we find them so incredibly attractive. Okay, so symmetry is not only a key idea in geometry, but throughout mathematics. Yet it is in geometry that it achieves its most immediacy. Okay, so it's a big idea in maths. Symmetry can be thought of as a transformation of a mathematical object which leaves some properties invariant. Okay, think of the parabola. Think of a square. If you cut a square along its diagonal, what remains invariant? What changes? An example from plane geometry is that all the essential properties of a parallelogram can be derived from the fact that a parallelogram has half-turn symmetry around the point of intersection of its diagonals. Okay? So that means if you take that center and you chop it and you rotate it, there's symmetry, there's rotational symmetry in that diagram. We get various kinds of symmetries. We get rotational symmetry, we get symmetry in a point, we get line symmetry. So it's a big idea. Symmetry is frequently used to make arguments simpler and usually more powerful, and is also a key organizing principle in mathematics. Just think about if you have a parabola that cuts the x-axis and you have the axis of symmetry in one root. You don't have to solve it to find the other one. You use the fact that the roots are symmetric in the axis of symmetry to find the other coordinate for the x-intercept. In geometry, if you work with analytical geometry and you've got a figure that's symmetric in the y-axis, you use that symmetry to find coordinates of the vertices of that figure. Okay, so folks, please, for example, here we say, probably the best way of defining quadrilaterals, except for the trapezium, is via their symmetries. Think about in algebra, the hyperbola. It's symmetric in its asymptotes, the rectangular one. Oh, sorry, not in its asymptotes, in the center. So that means, in the origin, if you have point AB, point BA is on there, on the hyperbola. Point minus A minus B. Point minus B minus A. Variations, 8 variations of that one coordinate pair is based on symmetry. The same with a circle. Okay, so folks, please, it's a huge idea, and always remember that when you teach and you can identify symmetry, talk about it. The third big idea in teaching and learning of geometry is the notion of transformation. Transformation permits students to develop broad concepts of congruency and similarity and apply them across figures in the geometry classroom. For example, congruent figures are always related either by a reflection, a rotation, a slide or a glide reflection. Figures that are congruent, remember, that's what we're talking about. Studying transformations can enable students to realize that photographs are geometric objects, that all parabolas are similar because they can be mapped onto one another using a particular transformation. If you look at the sine and the cosine graphs, they are congruent. Matrices, for instance, have powerful geometric applications, and so on. In fact, we use matrices to perform transformations on geometric figures. That's how powerful this idea of transformation is. Transformations also play a major role in artwork and in many cultures. For example, they appear in pottery patterns, in tilings, in wall decorations, in friezes. There's so much more that we can say about where transformations appear in the real world. It's all around us, folks. Look at that first figure over here. That's a tessellation of little parallelograms and squares that have been tessellated onto a plane to form something visually appealing as what you see over there. The same thing happens here. We've got the triangle, the Star of David, you can see hidden in there. We've got these two triangles. Inside the triangles, we've got circles that are intersecting. In those intersections, we can create art by putting different colors in there. Another place where you will find geometry around us, let me go back there, is in GPS navigation. GPS navigation works on geometry. It's the globe that has been divided into geometric points and locations in 3D that helps us to navigate our way around the globe. If you look at a 3D projection of a movie, that projection is a combination of geometric ideas. When you see it through your lens, it appears as a 3D shape. Why? Because the geometry in the original 2D projection of that shape created the way the light bends and forms a 3D shape. Even if you think about the latest technology that is used by organizations around the world, Mossad, the FBI, the CIA, huge investigation organizations to do facial recognition. If you walk through, you don't have to put your finger on a scanner anymore. It scans your eyes or it scans your faces and it recognizes you as Jacques Duplessis entering the building. They have managed with facial recognition to find criminals that's been eluding justice for years by just scanning their faces into a database. When they are in a particular place, they are recognized. Okay, all of that, folks, are geometry. So it's exciting stuff that we're going to be looking at. There is geometry all around you. Become aware of that and exploit those ideas. As a teacher, take it into the classroom. The three big ideas informing geometry. Okay, folks, I hope that got you excited for what's coming next in our video series, which will be the Van Hille levels and the Van Hille phases of learning. If you learned something as a teacher from this video, please like it. Feel free to comment in the space below and also subscribe to my channel where you'll get updates when I post new things.